This is the next video in the series about the strength of acids and bases. We have talked about strong acids and bases, then we talked about weak acids and bases, and now we're going to talk about acid-base conjugate pairs and how one member of the pair has to be stronger than the other one and how to figure out which one is stronger. So we talked about conjugate acid-base pairs at the very beginning of the chapter. So here's an example of one. Ammonia and the ammonium ion. So remember that an acid is the one that donates the proton, so it's the one that has more protons in it. So this is going to be our acid, the NH4+, and NH3 is going to be our base. And if we think back to our strong acid and base list, we do not remember these being on there, so these are both going to be weak. Weak acid and weak base. And just knowing that it's weak or strong is helpful because we know how difficult our ice table is going to be to solve, but I'd really like to know how weak we're talking and which one of these is going to be stronger, and whether when I encounter this in the wild, is this going to be basic or acidic? So I really want to know which one of these is it stronger. Is a mixture of this going to be an acid or a base? And so we can figure this out by relating the Ka value to the Kb value. So our Ka value goes with the acid, which is NH4, and we can write the acid ionization equation, our favorite thing. Only it was a little bit shorter, it would be faster to write. Okay. So the acid equation has a Ka for the acid ionization. Okay, and then we've got base ionization for the other one. And that's going to give us our Kb. And NH3 is our base. Mix the base with water, and it will sometimes form conjugate acid and hydroxide. Beautiful. Okay, so I'm trying to relate these two numbers together so we can add these expressions to get a total, and we are pleased to see that some of this interesting stuff cancels. So an NH3 is present on both sides, and NH4+ is present on both sides. So all we're left with is the boring stuff. All the information about water. 2 water molecules plus equals hydronium plus hydroxide. And I really do hope that this looks familiar. This is about the 3rd time we've written this. It's the auto ionization of water. Water acting as both an acid and a base with itself. We named that Kw for water. Wow, that's cool. If you add the Ka and the Kb expressions together, everything interesting cancels, and you always end up with the expression for water. And remember, from the equilibrium chapter, when we add 2 expressions together, we can get our final value for the equilibrium constant by multiplying each of the steps. I knew there was a reason we covered that. So the Kw is going to be the product of the Ka and the Kb. And remember, we know the value for Kw. It's 1 times 10 to the negative 14th at 25 degrees Celsius. Awesome, and that is for a conjugate acid-base pair. You cannot simply multiply any Ka by any other Kb. That's not how it works. It has to be the Ka and the Kb for a conjugate pair, a protonated version and an unprotonated version. Those Ka and Kb are complementary. Okay, so now we know how they're related, and that relationship is going to tell us about which one of these two pieces is going to be the strongest. So the strengths are related to the Ka and the Kb, and they are related to each other. How are they related? Well, if you multiply the two of them, you end up with a constant. So that means that if you increase one of them, you have to decrease the other. So they're inversely proportional. There are an awful lot of inversely proportional relationships in this chapter. Okay, so if they're inversely proportional, that means that as one of them gets stronger, the other one is going to get weaker. So here's what it says in your book. The stronger the acid or base, weaker its conjugate partner. This is definitely not relationship advice in any way, shape, or form. Advice only for acids and bases. Okay, so you've got one piece, either an acid or a base. As that first piece gets stronger, the second piece is going to get weaker. So we can look at that with this little table that I've made. We can look at it for strong acids, weak bases, and strong bases. And so we'll look at the acid and the base in each pair and identify which one is going to be stronger and which one is going to be weaker. Give you a minute to catch up writing that. Okay, so here's an example of a strong acid, HCl, and acids donate their protons. So if this donates its proton, we'll be left with the conjugate base, Cl minus. And in this pair, we know it's a strong acid because we were dutifully memorizing the table. So our acid is going to be very strong, and that means that our conjugate base is going to be very weak. The stronger the acid, the weaker its conjugate partner. Okay, let's try a strong base. My favorite strong base is sodium hydroxide. And strong bases, by one definition, donate hydroxides. So the conjugate acid is going to be just the sodium ion. And so if sodium hydroxide is a very strong base, then its conjugate acid is going to be very weak. Stronger the base, the weaker its partner. All right, and let's check out our weak acids and bases. So you may not know any weak acids and bases by heart yet, but we have been using this weak base up here a lot. So we can use NH3 as our weak base. Weak bases accept a proton. So adding a proton would give us NH4 plus for the conjugate acid. And in this case, NH3 is the stronger base. Usually we talk about ammonia as a basic compound. And if NH3 is stronger, its conjugate acid is going to be weaker. And then your newest, most favorite weak acid that is in so many examples in this chapter is acetic acid, formula H2CO3. Acids donate protons, so if we take a proton away, we get HCO3 minus. It can also donate a second proton, called a polyprotic acid. More on that later. So this is a weak acid. So the acid is going to be the stronger piece, and the conjugate base is going to be the weaker piece. Okay, the table is all very well and good. We understand qualitatively the relationship here. One strong piece is going to have a much weaker partner. A weak piece will have a much stronger partner. But remember that when we're talking about how strong something is, we're talking about these values. How strong something is related to how big the Ka or the Kb is. So in your book, and in every book, at the back, there will always be a table that has a bunch of Ka values for different acids. So here's one that I pulled off the internet that I particularly like. It's probably so small that you can't read much of it, but you should at least be able to see we've got the names of the acids, we've got the formula for the acid, the formula for its conjugate base, its Ka value, and its pKa. And so I'll just give you the short version since you probably can't see a lot of what's going on. You can just listen to my beautiful voice as I explain it. So here at the top half of the table, we have our strong acids. And in the Ka column, you can see that it's blank. They haven't even bothered to list a Ka because Ka equals huge. It's so big we don't even bother to measure it. At the other end of the acid scale, down here at the bottom, we have our strong bases. They are such poor acids it is not even funny. And their Ka value is essentially 0. They are really bad acids because they are bases. And then in the middle, we have all other kinds of weak acids and bases. And remember that we draw the line between acidic and basic at 10 to the negative 7th. And I'm sure you can't read it, but I will draw the line here. In between 10 to the negative 7th and 10 to the negative 8. So above 10 to the negative 7th, I'm just going to write it on top of this since you can't read it anyway. Ka greater than 10 to the negative 7. Those are going to be weak acids. And if the Ka is less than 10 to the negative 7th, it's going to be a weak base. And the reason that I showed you this giant table that you can barely read is to remind you about what the Ka means for its strength and what it means about the strength of its partner. So over here, we're somewhere between Ka equals 10 to the negative 7th and Ka equals huge. I realize that's a large range, but let's just say that Ka is fairly large. So we have a large Ka. That means we have a stronger acid and we have a weaker conjugate base. Because a large Ka means we have a strong acid, and the stronger the first partner, the weaker the second partner. If we go down to the other end of the acid list, where the acids are truly terrible, our Ka is going to be very small, somewhere between 10 to the negative 7th and 0, admittedly a wide range. But if we have a small Ka, we're going to have a fairly weak acid, much weaker than the strength of its conjugate base. And it feels a little odd to call these conjugate bases because usually we would call it a base and a conjugate acid. The base is the most important part at the small end of the Ka scale, and the acid is the most important part at the large end of the Ka scale. Okay, so more on numbers later, but first we have to answer our original question. Which one of these two things is stronger, NH3 or NH4? We're all about petty feuds here. All right, let's see. So we said NH3 was a weak base. And we said NH4 plus is a weak acid. And on that ginormous table that you cannot actually read, partially because I wrote all over it, right here, ammonium is listed in the table, and its Ka is listed as 5.6 times 10 to the negative 10th. So usually when you get a table, only one of these two numbers is written in it. But remember, we can convert between them. We can convert between Ka and Kb using 10 to the negative 14th, our value for Kw. And so if we do that and we take 10 to the negative 14th over 5.6 10 to the negative 10th, you should get 1.8 times 10 to the negative 5th. And 10 to the negative 5th is closer to 0 than 10 to the negative 10th. So that means NH3 is going to be the stronger piece. So we think of this compound as basic because the weak base is stronger than its conjugate acid. So that has been a discussion of conjugate acids and bases. Remember that no two pieces are going to be equal. One piece is always going to be stronger than the other one, and the K values will tell you how. So in the next video, we'll talk about ice tables and how to calculate precisely how much the concentrations change and how much dissociation happens in solution.